I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain,
life, the universe.
This week, how your gut bugs are linked to healthy aging, virtual reality becomes a reality for a fish, and how scientists have solved a 3,700-year-old mathematical mystery scratched into a clay tablet. Plus, can science prevent catastrophe and the end of the Earth? Hello, I'm Chris Smith, and this is The Naked Scientist.
The Naked Scientist podcast is powered by ukfast.co.uk.
And up first, as is customary here on The Naked Scientist, a look at this week's breaking news stories. And first this week, over the next 40 years or so, scientists are predicting that the elderly population in developed countries is going to increase by about 350-fold, and that will place a very significant burden on healthcare. But can we help people to age better and to remain more independent into their older age? According to Emory University's Daniel Kalman, the answer is yes. And that's with the help of the right bacteria in the intestine. He's been studying a kind of worm called C. elegans, which either did or did not have gut bacteria that were producing a class of chemicals called indoles. Worms that did have the indoles didn't live longer, but they did age much better than worms that didn't have those chemicals, as did flies and even mice.
So there's been a long tradition in the worm community for studying aging. These animals live 21 or so days, so they can be studied pretty easily, more easily than humans. And we can feed them bacteria or bacteria mutants, that is bacteria that lack certain genes, and then we can understand what their responses are relatively quickly. To measure health span, we look at how well the worms move. As they get older, they move less well. And we began to work with bacteria that produce particular molecules and ask, well, could these bacteria cause older worms to move better?
So your rationale is if we knock out a certain factor from the bacteria and the worms show accelerated aging or they're more frail, that molecule coming from those bugs might be involved in the aging process.
Correct. The molecules that we've identified don't actually affect the lifespan of the animals. They do affect the health span, that is their capacity to move, their capacity to reproduce, the capacity to do a lot of the things that we associate with health versus aging.
And what are those molecules?
The molecules are in a class of indoles. They're made by plants. They govern root growth in plants. They're made by lots of different kinds of bacteria, including probiotic bacteria, and affect the way bacteria talk to one another, and they also affect us.
So if there are bugs that make these indoles in the intestines, the animals are healthier. If the bugs don't make these indoles, the animals don't live any longer, but they are less healthy. They don't age as well. Do you know what the indoles are doing to the worms' bodies to exact that change?
We do. We were able to identify particular receptors for these indoles, and we think this molecule, which we call AHR, recognizes indoles and regulates gene expression to produce this healthy aging effect.
That's worms. What about more complicated creatures like mice or like humans? Do you think the same effect is going to happen there?
We tested that in the paper, and we did look at these effects in higher organisms, that is flies and mice, and we saw the same kinds of things. With indoles, worms move better, flies climb higher, and mice are better able to tolerate stressors. And geriatric mice, these are mice that are very, very old, also move better.
Did you try the experiment where rather than get the bacteria to give these animals these indole molecules, you just gave them the indole molecules without any bacteria, which would prove that the indoles do appear to be doing this? It's not some other factor coming out of the bacteria that's doing it.
Yeah, so we also can provide the molecules specifically to animals, which we did in worms, flies, and mice. And these molecules by themselves are sufficient to produce these protective or health span increasing effects.
So, moral of the story, look after your gut bugs if you want to age well. That was Daniel Kalman discussing the work he's just published in the journal PNAS. Now, speaking of wanting to live long and prosper, do you remember the holodeck that appeared in some episodes of Star Trek? That was the virtual reality room that could turn into anything that you could think of. Well, this week scientists have actually made one, but before you get too excited, it's not for humans. It's for animals. This new virtual reality room can help scientists to run experiments that they couldn't before, testing how animals understand their environments. And that's something that's been very tricky for free-moving animals, like, for instance, a fly. How would you get a fly to wear a virtual reality headset, for example? Andrew Straw, who is Professor of Biology at Freiburg, materialised in front of Georgia Mills to explain how and why he did it.
I've always kind of been inspired by the holodeck of Star Trek. So basically what we did is we made an arena where animals can go in, and we track them as they move around in 3D, and we track them almost instantaneously. And then based on the position of where the animal is, actually where its eye is, then we draw with computer projectors on the walls of the arena everything we need to draw so that from the position of that animal, it sees whatever kind of virtual world that we want, because basically the animal's in a computer game. And then the real trick is not just that we do that once, but that we then update the position of the animal and we update the world. So it's a completely dynamic process. When the animal moves around, what it sees is completely consistent with it being really inside this computer game. So to the animal, it's immersed in this 3D world that it can see.
I see. So it's a holodeck for animals. So the animals in this environment, can you make it as if there are obstacles in the way? It's not just sort of running around in the space looking at the walls. It does look as if to it there's stuff in the middle.
Yeah, exactly. Some of the first experiments that we did were kind of validation experiments where we could test how an animal would behave. And we did this with flies and fish. We put in just a simple vertical post, a cylinder, in the middle of the arena, a real one, and we just quantified animal behavior with the same tracking system. We just measured how they swam or flew around this post. And then we could do that same thing, not with a real post, but with a virtual post. And then we could calculate those same statistics again, and we could see that the animals behave indistinguishably to the virtual post as they do to the real world post. And so, yeah, I think it's fair to call this a virtual reality for the animals.
What animals can go in it? Because animals have very, very different visual systems from each other. So does it work on all of them?
You're completely right that animals have very different visual systems. For example, our displays are kind of tuned for humans. So in terms of the spectrum, the colors, we use the RGB for humans. And that works pretty well for the kind of experiments that we've been doing and that we're interested in. But, a lot of animals are sensitive to ultraviolet, for example. And we would have to think about some kind of modifications or different display technology if we wanted to really give a good virtual reality in the ultraviolet spectrum. But in terms of what kind of animals, we're really interested in model species that are used commonly in neuroscience. And so those are rodents, fish like zebrafish, and Drosophila, fruit flies. Those are the ones that we've spent the most effort testing.
What kind of research do you foresee people doing with this?
This technique really allows people who are interested in studying interactions between, an animal and its environment, or an animal and other animals, to do kinds of experiments that they weren't able to do before. There's the area where I kind of come from, which is the interaction of visual processing with, let's call it higher level processing, like spatial cognition. So how does an animal know where it is and what it's seeing. And you can imagine that by being able to play games with an animal, like have it teleport from A to B, we can ask, for example, is it building a map of its environment or not? People have historically been doing experiments on freely moving animals, and there, of course, it's very difficult to control the visual world. Or they've been doing these restrained animal virtual realities, and there the feedback that the animal gets is not natural. And so the innovation here is doing free-moving virtual reality.
I still want to have a go, though. It sounds terrific. And actually, that research is all open source, so researchers can use it for their own virtual reality experiments. Andrew Straw, whom you heard there, was speaking with Georgia Mills about the work he's just published in Nature Methods. You're listening to The Naked Scientist with me, Chris Smith, and still to come, why Pythagoras was beaten to his own theorem by 1,000 years, and, when the end is nigh, will science be able to save the day for us? Before that...
What happens when the science and technology of space comes down to Earth? This is Down to Earth from The Naked Scientists, where we look at how the technology and science developed for space is used back on planet Earth. I'm Dr. Stuart Higgins, and today we're talking about how the mathematics used to spot X-rays coming from exploding stars can also be used to catch the early signs of skin cancer. On June the 1st, 1990, the German Aerospace Centre with the UK and US launched Rossat, the Röntgen satellite. It was designed to allow researchers to search for X-rays coming from across the universe. However, scientists needed a way to identify the faint traces of X-rays from the data the satellite was producing, a bit like trying to hear a voice under a background of static. They needed to separate the signals from the noise. This led researchers at the Max Planck Institute for Extraterrestrial Physics in Germany to develop the scaling index method. It's an analysis technique which identifies structures from within a dataset. Imagine a digital photograph of the seaside, a beautiful golden beach, the sea lapping at the shore. The scaling index method would take each pixel in that image, draw a circle around it, and check to see whether its neighbouring pixels look similar. The algorithm then uses that information to work out whether the pixel belongs to, say, a straight line, like the horizon, a flat plane, like the sky, or a point object, like a seagull up above. Now imagine the same scene, but on a grey and cloudy day. It's tricky to see that seagull. The algorithm's power is that it can still pick out the seagull from the noise of the grey clouds. But this algorithm could be applied to more than just astrophysics, or indeed seagull spotting. The same researchers in Germany teamed up with medical doctors to invent a system for spotting the early signs of skin cancer. Skin cancer can look like a darkening in the pigmentation of the skin and can be challenging to properly identify. In their system, doctors can take magnified digital images of a patient's skin and apply the scaling index method to identify subtle changes in the colour and variation. The algorithm is able to score how likely the variation is due to melanoma, a type of skin cancer. The big advantage is that the doctor doesn't need to be an expert in melanoma in order to use the system. The algorithm does the work, helping the doctor make an accurate diagnosis. So that's how the mathematics of spotting X-rays from exploding stars is being used to help identify skin cancers back on Earth. That was Down to Earth from The Naked Scientists, and join me again soon to learn about more space technology that's changing lives back on Earth.
And thank you very much, Stuart. Next time on Down to Earth, Stuart hears how NASA helped heart surgeons to develop a much better pump for patients needing a transplant. And it's very timely and pertinent because this year marks 50 years since the first ever successful heart transplant. Now, back to Earth and backwards in time, because an ancient mathematical mystery has been solved this week by two Australian researchers who've been studying a 3,700-year-old clay tablet that was made originally by the Babylonians. It was first uncovered about a century ago in what's now southern Iraq, and then it ultimately was left by the owner to Columbia University in America. Historians knew that the writings on the tablet were numerical, but they didn't realise their significance. Now, mathematicians Norman Wildberger and Daniel Mansfield from the University of New South Wales in Sydney have deciphered what they think is the true meaning of the tablet, and it describes, they reckon, a previously unknown form of trigonometry for finding the sizes of right-angled triangles. And, get this, it predates Pythagoras by 1,000 years. Izzy Clark caught up with Daniel Mansfield to hear what the tablet looks like and what it shows.
It's rectangular, it's surprisingly heavy, and it's written in a very neat hand. Someone went to a great deal of trouble to rule this thing out neatly and carefully write down a whole sequence of numbers. The tablet was obtained by George Arthur Plimpton, who was an American publisher, and it was sold to him by a fellow called Edgar Banks, who's the real person upon which they say Indiana Jones was based. He was a archaeologist, a academic, an adventurer, an obtainer of rare antiquities. He's even got the same hat. So he sold it to Plimpton, who was a publisher and a collector of ancient mathematical texts. But of course, Plimpton just knew it had maths on it. No one really understood exactly what this was about. But it really wasn't known that it was anything special at all until in 1945, when Neugebauer and Sachs discovered that it actually contains Pythagorean triples.
And what exactly are they?
They're three numbers which describe a right triangle. Now, numbers which describe a right triangle are very special because they obey what we call Pythagoras' theorem. So if you have a triangle with sides A, B, and C, where C is the hypotenuse, then the numbers are related. A squared plus B squared is equal to C squared. And what Neugebauer and Sachs showed was that Plimpton 322 actually contains Pythagorean triples, which is amazing because it shows that the Babylonians knew about Pythagoras' theorem 1,000 years before Pythagoras was even born.
I mean, that is incredible. What do those numbers mean?
Well, that's what people have really been scratching their heads about. For 70 years, we've known that this is a very special, highly sophisticated tablet, but why does it have Pythagorean triples on it? What is the meaning of it? It's not just a random sequence, it's an ordered sequence of Pythagorean triples. And the ordering is very special. It starts with something that's almost a right isosceles triangle, or almost half a square. And then it goes down row by row to flatter kind of triangles. I don't want to say words like inclination or angle because they don't exist at this time. The triangles get flatter, if you like.
Now, Pythagoras' theorem, which we all learned throughout high school, uses angles. If they weren't using angles, how did Babylonians use trigonometry?
They used ratios. So this is 1,000 years before angles were even thought of. But you don't need a notion of angle to study trigonometry. You can use ratios alone, and in fact that's what we propose Plimpton 322 is all about, just a table of ratios of the sides of a right triangle. They'd use ratios to describe steepness. So you see things like descriptions of a canal, or they talk about how much width per unit depth the triangle requires. So a long ramp might require a lot of width per unit depth. And a really steep one, we call it steep, and the Babylonians would say that it's a very short amount per unit depth.
How did these Babylonians use trigonometry?
It's very difficult to say what they used it for. We really don't know. All we have to explore this world is this tiny window for which we have evidence. Now, we have something which appears to be a trigonometric table, but how they used it is really open to speculation. I'm happy to speculate on that. Personally, I think it was used for surveying, but I have to say, all that we have is what's written on the tablet.
This is all mathematics from literally over 3,000 years ago. Can we use this new, well, not new approach, this ancient Babylonian approach for our use?
Well, I'd love to see us find a way to use this trigonometry. It's really out there for people to start using it again now that we know what it looks like. I personally think that we should use this to teach trigonometry in school. This is a great way for people to understand triangles, and it doesn't require them to understand what the square root of 2 is, or trigonometric functions like sine, cos, and tan, or an angle. You can study triangles without any of these things. It's very early days. We've only just discovered this, or rediscovered this. Certainly, I think there's a place for it in the world.
Incredible, isn't it? A wonderful story how old 3,700-year-old maths could become new maths in the classrooms of today. Daniel Mansfield was speaking with Izzy Clark, and the story he was describing is just out in the journal Historica Mathematica. Now, back to the future. I suppose you could say. And you may have seen recently the story about tech leaders and heads of robotics and artificial intelligence organisations penning an open letter to the UN, the United Nations, requesting that they think very carefully about AI, artificial intelligence's place in the future of conflict. But why are they worried? Tom Crawford has been investigating.
The hit 1970 song War famously asked, "War, what is it good for?" And the answer, of course, was absolutely nothing. Whether or not you agree with Edwin Starr, war has always happened throughout human history, and chances are it will continue to do so in the future. With this in mind, it's important to ensure that if it does occur, it's carried out as humanely as possible, which is why treaties such as the Geneva Convention exist. Violating certain parts of this treaty, such as the use of chemical and biological weapons, for example, constitutes a war crime. With recent developments in artificial intelligence, a new version of the convention may be required. In an open letter to the United Nations, more than 100 leading robotics experts, including Elon Musk, Stephen Hawking, and the founder of Google's DeepMind, have called for a ban on the use of AI in managing weapons systems. Peter Clark, founder of Resurgo Genetics, is an expert in machine learning.
The aim of this article was to try and head off the possibility of an AI arms race. So where you start to develop these technologies, and as most of the people developing these AI and robotic technologies, they have no wish to create killer robots. But once this technology is in place and becomes a massively powerful tool in the suite of armaments that a nation state or other actors have to fight warfare, these will inevitably get used. So what it's trying to do is to try and trigger a debate about having international legislation, much in the same ways that you have with nuclear weapons or chemical weapons. And we need to start thinking about a similar type of international level legislation for these autonomous weapon systems, because they are going to transform the nature of warfare, and we need to prepare for that.
We currently have not quite fully autonomous killing machines, but I feel like we're very close in some of the technology that currently exists. For example, drones, which are flown via remote control from a pilot in one country and can drop bombs, which of course will kill people. So how are these autonomous systems different to something like that, which still has the human element?
Well, with the human element, you're always subject to your own personal morality and ethics, that even if you happen to be separated by many thousands of miles from these events, you still realize and have that capacity to understand that you're destroying people's lives. With an autonomous system programmed with a particular set of objectives, you're removing that human moral and ethical constraint on the behavior of those systems. And as soon as that's lost, we enter a very, very different world.
Intruder! Intruders must be destroyed!
Is this a case of a robot, say, with a gun, just walking around and shooting people that it thinks are a threat or that are enemies?
Well, this is the interesting thing, and I think that we've all have these images from Terminator and other films, which is these sort of lumbering great robots who are hunting people down, but actually the reality can be very different. So what you may have is something along the lines of swarms of mini little autonomous drones carrying small packets of explosives that could target individuals in a population. So you could have swarms of millions of these things sweeping over cities. So very many different realizations of the applications of this type of technology. But we know that in whatever form, they really will transform warfare.
How would such an autonomous system even go about knowing specifically who to target?
So I think much in the same way that, for example, credit reference decisions are made nowadays, where you're aggregating information on people's previous payment histories, and maybe now as marketing gets more and more targeted, where you can build up very, very precise profiles of who people are in an autonomous way and target them autonomously for advertising. These same types of techniques can be used to profile people in all sorts of other ways. And you could imagine a situation in the future whereby an authoritarian regime could use this same type of targeting and profiling of the population to target individuals in that population that were a threat to those power structures and have the entire chain not be subject to any human decision. So it's really taking all of the technologies that exist now in terms of your robotic weapon systems, tying those into these tools that allow very precise profiling of a population and tying these things together. And so this is not talking about technologies that are far off sci-fi future fantasies. These are talking about technologies that are available now and could be put together now into a system which could be catastrophic for the globe.
Chilling, isn't it? And as Bill Gates has famously said on this subject, I don't understand why some people are not concerned. Peter Clark was talking with Tom Crawford, and in part 2 of the programme we'll be hearing more about some of the world-ending risks, like the threat from AI, that scientists are looking at and how they're trying to prepare for them. You're listening to The Naked Scientists. I'm Chris Smith, and if you'd like to get in touch, you can tweet at Naked Scientists, you can find us on Facebook, or you can email chris@thenakedscientists.com. And now it's time to hand over for this half of the programme to Connie Orbach, who wants to paint a rather scary picture for you.
New York is underwater. AI robots have enslaved humanity, and genetically engineered mosquitoes have led to an airborne super malaria. No, this isn't the start of Hollywood's next apocalyptic blockbuster, but a just about possible vision of the future. And in this part of the show, we're going to be delving into the world of extraordinary catastrophic risks, asking, if the worst happens, does science have our back? I'm Connie Orbach, and this is The Naked Scientists. To start us off on our journey, let's hear from the experts.
My name is Sean O'Hegarty. I'm the Executive Director of the Centre for the Study of Existential Risk in Cambridge.
Yep, that's right, because these are all examples of existential risk. The type of thing that, if it did happen, might knock humanity out completely.
Risks that might threaten human extinction or the collapse of our global civilization.
Sounds pretty scary, right? The threatening of our human extinction, but don't worry.
Most of the risks that we look at are high impact but quite low probability. Now, they aren't all, and climate change is an example of one that's quite high probability, I think. It's likely that we will see more global pandemic outbreaks that will cause deaths of millions of people, like the Spanish flu did in the last century. And then there are things like, for example, it is entirely scientifically plausible that we would be hit by a meteor the likes of which wiped out the dinosaurs. But the last one of those that hit us was 66 million years ago, which, if you think about it, is 660,000 centuries. So the likelihood that it's going to happen in the next century is vanishingly unlikely. So we tend to think of ourselves as, in some ways, an insurance policy. When the stakes are so high, when the consequences are so big, we think that some people should be working on these things. It's not necessarily what everybody in the public should be worried about, in the same way that it would make sense for you to take out insurance in case your house burnt down, but you shouldn't be worrying about your house burning down all the time. You should just be taking the precautions of not leaving the oven on.
Phew. So it's just an insurance policy. And luckily, we have clever insurers like those at the Centre for Existential Risk, otherwise known as CSER, and they're willing to take out cover. Then, they and others like them can feed back to science and policy, and soon enough, we'll all be on a fully comprehensive plan. I's dotted and T's crossed. Goodbye, existential risk. Well, of course it's not that easy. Not least because that would be the end of the programme. But also, science as it stands just isn't that set up to deal with or predict these sorts of catastrophes. And really, CSER is just a small outpost fighting against a sea of traditional scientific practice. Sean's colleague, Adrian Curry, laid out the issues for me.
The worry with existential risk is that thinking about these low probability, high impact events involves a bunch of features which make science as it's currently set up really ill-equipped to deal with. So I'll really quickly sort of list those for you. So first, you're dealing with unprecedented events. So you don't have any evidence, in a sense, right? You don't have any analogies. If with big rocks hitting the Earth, we know that big rocks hit the Earth in the past. We can go and look. With, I don't know, robots becoming sentient and chasing us around or something like that, we don't really have any analogies for that. So it's very hard to have much evidence. And this means that your science is going to have to be speculative. What you say is almost always going to be wrong. What you say is almost always not going to have the kind of evidential support we expect scientific, say, publications to have. And so there's a way in which, in order to do this scientifically, to get the ball rolling, to start figuring out what the landscape is like, we need to pull back some of those standards about what good science looks like, and perhaps have different standards. So instead of saying something like, this deserves to be published because it's got a positive result which has met my criteria for statistical significance, we might say something like, this deserves to be published because it opens up an area that we haven't thought about very hard yet, or it gets something wrong but in a really importantly interesting way, or it has a negative result in it, or a set of negative results. And these are kind of different criteria for success. And I think if we're going to start thinking systematically about these kinds of events, that requires this sort of speculative thinking.
So you see the problem. We have these big existential risks, and if they did happen, they would be really, truly catastrophic. But they're also really unlikely and unpredictable, and science, which rewards getting things right, pushes people to do things which are likely and predictable. And because of this, no one really wants to look into existential risk. In fact, it's a bit of a career downer. Here's Sean again.
I guess you can divide the people who are thinking about this into two communities. One is the community like our centre and other centres like them who have a specific remit to sort of think the unthinkable, if you will. And we're allowed to be a little bit sort of exploratory and a little bit weird, and that's fine. But then there's a whole other community, which is people who have skin in the game, who are really involved in these emerging sciences, and who will sometimes feel like they need to either raise concerns about a particular consequence from a scientific trajectory, or who will have an idea that might provide a global solution, but that might overturn an existing set of theories. And I think it's particularly challenging for those people. One example might be in virology research in the last decade or so. There's been a lot of debate about the importance but also the potential risks of doing research to modify the influenza virus. And for a number of years, several individuals were raising concerns about both the accidental release from laboratories of modified pathogens and also the potential risks of publishing this research because it might give bad people bad ideas. And I think that's a very challenging thing to do, because if your whole scientific community is doing this because advancing our scientific understanding is a good thing, but secondly, this helps us provide tools against natural pandemics, it's a very hard thing to stand up and say to your colleagues what you're doing might actually pose as big a risk as the solution it poses. It puts those people in a very uncomfortable position where they may upset their peers, they may alienate the funders who might support their own work, they may even bring their own field into disrepute by causing a sort of public panic about certain types of research. And so I think that makes the role of these people who either have a new idea that overturns existing theories or have a new concern that sort of pushes against the prevailing ideas in the community that they're around. I think that's a very challenging but a very important position to be in.
And when people do, they often get labelled as cranks. There's the 1% of scientists who think climate change is a myth, or the proponents of traditional Chinese medicine. In fiction, there's Back to the Future's Doc Brown, and from history, there's the many scientists whose names have been lost to the passage of time. But also those who, though rejected initially, were later proven to be right. Galileo and his predecessors who suggested that the Earth orbited the Sun, or Darwin and his theory of evolution. These figures populate our myths and media. Sometimes they're wrong, sometimes they're right, but either way, they're nearly always dismissed. So there's two problems here. One, How do we make science more open to these sorts of people? Let's call them Mavericks, so they can think outside of the realms of normal science and help us spot and mitigate existential risk. And 2, how do we tell who's crazy and who's correct? Well, first of all, we don't call them crazy.
What we're trying to deal with is the fact that some of them are people we need to listen to. And so using terminology like crazy, which is the sort of terminology we use to push them aside, is what we need to try to avoid doing.
Oops. Sorry, Hugh. Good point. That's Hugh Price, Academic Director of Cambridge's Centre for Existential Risk. He's been pondering a solution. Working title, The Maverick Room.
What we need are scientific and technological whistleblowers, kind of people who are thinking in a slightly abnormal way. They see something that other people don't see. And we need to make it possible for them to put up their hand and get listened to in those sorts of circumstances. What tends to happen, as we know with whistleblowers in other fields, is that they get attacked by their peers. They get marginalized and ostracized. The idea of what we call a maverick room is we're interested in the question as to whether it be possible to create a kind of safe space where instead of the norms and sociology of science pushing these people out, it created a space in which they could be listened to.
Talk me through this. How would this maverick room, this safe space look? Is it a physical building? Is it a internet chat room? What are the kind of practicalities around this? What can I imagine for this space for Mavericks?
So there's no reason for it to be a physical space. So what needs to happen is that to get into it, the Mavericks need to get a certain kind of recognition. So they need to pass through some sort of competitive process. Suppose that there's 10 British Mavericks every year. And so they get this little prize. They're one of the 10 Mavericks of 2017. And that prize comes with status. Hopefully there'll be some heavyweight scientific institutions backing this. They would then have the backing of those institutions. Somebody who wants to criticize them will be criticizing the institutions. Now, of course, people may want to do that. You can imagine the Daily Mail having a field day. But there's something to push back. There's the reputation of the institutions that are standing behind it. And with that kind of protection, those people who've been through that selection process will not be able to be dismissed by their regular peers elsewhere in science.
Because that's the problem here is this kind of reputation idea.
Yeah, that's right. It's all about reputation. So what tends to happen, this tends to happen more when there's a sort of group of people who are following some piece of science which is dismissed by the mainstream. By following that, they damage their reputation, and you get what I call a reputation trap. So anybody else who even takes them seriously in the sense of just going over there to look at what they're doing risks falling into the trap themselves and being dismissed by the mainstream. And so part of what we're doing here is sort of deconstructing the reputation trap.
For Hugh, it's all about reputation and giving people a safe, respected place where they can try things out, protected from ridicule and risk. But this doesn't deal with my second problem. We still have to decide who's in and who's out of this safe space. How do we do that when everyone who goes against normal science has the potential to be a genius?
Exactly. And so if you just set up a committee and said, and in effect, some funding programs are doing this, because some funding programs are recognizing the value of encouraging innovation in science. And so they say, we want blue sky, out of the box, non-conventional thinking. But then they appoint committees who, of course, think in the conventional ways. And so it's very hard for those committees to actually pick the unconventional thinkers, or at least to pick them in a way such that they have a reasonable probability of picking winners. So somehow we have to find an incentive structure for the committees so they get rewarded when they pick somebody that an ordinary committee wouldn't have picked, but it turns out to have something important to say.
Still a few wrinkles to iron out there then, but Hugh's on the case. You're listening to The Naked Scientists, and this week we're asking if science is set up to deal with some of humanity's bigger risks. Hugh Price's idea of a maverick room seems like a nice, fairly simple way to encourage creative thinking in science. But who are these mavericks we're trying to protect? Well, Hugh Hunt, and that's a different Hugh, keep track, is an engineer at the University of Cambridge, and while he may not consider himself a maverick, his field is definitely a little controversial among scientists and non-scientists alike.
We're in a position with climate change that it looks like we're not going to meet our CO2 emissions targets, and we're going to have to figure out a way of cooling the planet, particularly a way of refreezing the Arctic because it's melting much faster than we'd like to think. And geoengineering is about man-made interventions in the climate.
Can you give me an example of the sort of man-made interventions we could be thinking of?
Geoengineering is divided up into two broad categories, SRM, which means solar radiation management, and CDR, which stands for carbon dioxide removal. Now, SRM is about reflecting the sun's rays back out into space. And we can make clouds whiter so that they reflect sunlight out to space, or we can put stuff into the atmosphere. It's been proposed that we emulate the effect of volcanic eruptions by putting sulfur dioxide up into the stratosphere, which volcanoes do, and that causes global cooling. We could do things like putting mirrors into space, a bit dramatic. These are all SRM, solar radiation management techniques. Carbon dioxide removal is about, well, perhaps we can get the oceans to absorb more carbon dioxide by making algae and so on grow more rapidly. So we could seed the oceans with iron filings or something. Or we could perhaps capture carbon dioxide from the atmosphere and pump it deep underground, carbon sequestration, carbon capture and storage. But all of these geoengineering techniques are big exercises, and they're quite scary because we'd be manipulating the climate.
What sort of reception do you find you get within this field for doing these sorts of things?
Geoengineering does seem to be a bit of a sort of Frankenstein science, and we tend to be categorized as being in some way evil. You know, why would anyone want to mess up our climate? But we're currently pumping about 35 billion tonnes of carbon dioxide into the atmosphere every year. That's about 5 tonnes per person on this planet every year. That's enormous. So the idea that we shouldn't consider doing something to clean up the mess that we've made, to me, that's what would be irresponsible. I think we ought to be looking at geoengineering as a responsible means of dealing with the mess we've made.
And what is the situation with geoengineering? I mean, we've said that it's not necessarily, people have a kind of negative idea around it, but is it still happening? Is there still research happening? What's the reality of the situation?
So geoengineering is, I think, inevitable, but unfortunately research in geoengineering is going very, very slowly. It's considered to be unwise to research technologies to fix the climate because maybe that's going to mean we'll take our foot off the pedal in terms of trying to reduce our emissions. Well, that's a fair, that's a reasonable concern. But the problem with that is that we will probably want geoengineering in 10 years' time, and we won't be ready to do it.
So what would you change so that you could be working on this?
I think it ought to be easier to do outdoor experiments on a small scale on geoengineering technologies. At the moment, it's almost impossible to do outdoor experiments without getting people concerned about the slippery slope that if you start with a small experiment in geoengineering, then you'll end up doing geoengineering full scale. Well, I think we just have to live with that as an issue because we've got to start these experiments to develop our insurance policy against us not achieving our targets for carbon dioxide emissions. What would I change? I think I would allow small-scale experiments at a scale of, say, 1/1,000,000th of full scale. And that would really help us move the science of geoengineering further forward.
As I said, pretty controversial. And the pros and cons of geoengineering are something that could do with a whole hour to themselves. But in terms of how science treats its mavericks, Hugh provides an interesting sample of one. Especially as, on the scale of existential risks, extreme climate change is fairly high up there as a likely possibility. So, if for the purpose of this argument, we decide that considering the possible impacts of things like extreme climate change, giant asteroids and unregulated artificial intelligence use, some fringe science is worth exploring, and there should be an outlet for people willing to battle against mainstream thinking, Is a Maverick Room really the right way to go about this? I mean, firstly, it's putting the responsibility for our salvation on only a handful of shoulders. Hugh Price suggested 10 British Mavericks a year. Seems a bit like saving a sinking ship by bailing out water with a teacup. And even if our ship isn't actually sinking, these sorts of risks are broad. Can a handful of scientists really be expected to spot every iceberg in the ocean? And finally, who are these Mavericks? The examples I've given and people I've interviewed so far are all white men. Does that in itself limit what we can do?
Diversity matters for science, especially diverse backgrounds, because people who have different life experiences notice different things in the world and they make different assumptions about it.
That's the University of California, Irvine's Kaylin O'Connor.
I work on things at the intersection of philosophy and biology and economics. The first primatologists studied male primates because they were men. And then when women joined the field, they studied the female primates and learned all these other things about it. So they made these kind of special discoveries motivated by their personal identities. In the case of existential risk, there can be cases where particular populations are at special risk. So if we think about global warming, for example, people who are on low-lying islands are at special risk, existential risk that is not necessarily threatening people in different countries. If those people on those low-lying islands don't have access to science, if they don't have social security or job security, if they're not able to join scientific communities, that might really affect the way we think about these kinds of risks. It might affect the sort of science we do about it.
So what can we do? What can we do to change that and to make it more open so that we can have more of these conversations?
So one thing that some people have pointed out as a good way to solve these kinds of problems are funding early career researchers, because young scientists tend to be more diverse than old scientists just as a historical sort of path dependency. There used to be more white people and men in science, and now there are more people of color and more women. So if you fund young researchers, they're going to be a more diverse bunch in general. A lot of people have pointed out that when you have the opportunity to set up some kind of discussion, so if you set up a Maverick Room, say, you have a lot of control over who you invite to the table. So in cases like that, you can just say, let's get different voices in the room, hear what different people have to say. Maybe that'll tell us about perspectives that aren't ones that would be obvious to us.
But also, if you have a Maverick Room, you're dependent on knowing who those people are already, and there's an issue there, no?
Yeah, sure there is. I mean, science and academia is based on networks of people knowing each other and who gets invited to conferences. And groups like that depends a lot on just who you know. And that's a challenge that is maybe hard to solve, but maybe it's a responsibility of people to try to at least look for other voices if they can to bring to their discussions.
Yes, our Maverick Room, as a safe space, would provide the protection needed for more diverse thinkers to speak out. But with science the way it is, finding those people in the first place might provide its own challenge. Is there a way to encourage creative thinking at a wider level? Remember Adrian Curry from earlier? He thinks there might be.
Well, I think one way of doing it is really changing the incentive structures that tend to create this sort of conservative science. So one of my colleagues, Shahar Avin, has really interesting ideas about funding science through lotteries instead of through peer review. So peer review is a process where, in effect, what you do is you write your paper or you write your funding application, and your peers, that is to say, other people, other scientists who work in the same discipline as you, who are experts in the same thing that you're an expert in, look at your work and basically say whether it's good or not, whether it ought to be published, whether it ought to be funded. One thing that seems kind of great about this is it encourages this kind of intersubjectivity, is the fancy word that we would use for people agreeing on stuff, right? That seems important. It builds consensus. But the problem is it also serves a kind of gatekeeping function. Often if you're a reviewer and you get a piece of work and you're like, this does not fit the usual ways that we do this, you're going to reject it. And so Shahar Avin's thought is, if you remove that aspect, and in fact you have lotteries determining funding, that means first, you don't have to spend too much time writing these annoying grants, but second, it's going to remove that incentive to be particularly pleasing to your reviewers. Right? So that's an example of how you might encourage this kind of maverick thinking without having people to have to be kind of anti-establishment or rebels or, antisocial in some respects.
So that all sounds very nice, and everyone likes a lottery. But that also sounds like you could end up with a lot of stuff being done, because there's a reason for peer review, right, as well. It's a quality control.
Yeah.
And if you've got a random lottery of science, that's surely going to cause you some issues with what science is actually being done. Also, for diversification of the type of science, you could end up with, you roll a dice 6 times and every time you get a 1, you could end up with everything clustered in one part.
You're absolutely right that a pure lottery doesn't look very nice. What you want is the ideal combination of these things. So again, I'm just drawing on Shahar's work here. One way you could do it would be to have a kind of lower bar. So you do have a review process, and the reviewers basically throw out a bunch of them. And then there are the ones that meet some agreed standard, relatively low bar, and there's maybe some that everyone says definitely yes to, right? So you can imagine there's the middle ones, the ones that aren't definitely no, the ones that aren't definitely yes. Do a lottery for those ones in the middle.
Enabling Mavericks more widely seems to deal with some of the problems of the Maverick Room, but practically it sounds much harder to put into action. Either way, encouraging scientists to think more creatively must be a positive move in a world that feels ever more unpredictable. However, as a way of combating existential risk, it does seem to be, well, a little belated. It appears to me that many of the existential risks we're talking about are risks related to new technologies, genetic engineering, artificial intelligence, and, well, the car. Should science be taking more responsibility for the work it puts out there in the first place? Heather Douglas from the University of Waterloo seems to think so.
Scientists, because all scientists so far are also human beings, also have responsibilities to think about the ways in which their work might be used to exacerbate existential risk, even if that's not what they intended to mean.
Well, I think we can agree that all scientists are human beings, but we can also ask, how do they practically go about taking responsibility? Because, let's face it, lots of science carries potential risk, but it also carries great potential benefit. We don't want this sort of work to stop now, do we?
Certainly scientists are also very much involved in efforts to, say, stem the tide of nuclear proliferation, the risk of nuclear war. Various sorts of national level scientists group have science and diplomacy efforts that are centered around some of these things. Science and human rights efforts. And I think that just that they're already having conversations about what are responsibilities for scientists, that the responsibilities for scientists are not just to produce new stuff and make new discoveries and offload it off into an utterly unprepared public, that's actually not such a great plan, and that even if taking more time and being more reflective about the implications of one's work and having more conversations about the shaping of it, even with non-scientists or scientists from other disciplines and expertise, slows science down, that is probably, at this point in time, a valuable trade-off. That it's better to be a bit more reflective and a bit more careful about the directions we take our scientific research, even if it means things don't move quite as quickly in most areas. And a lot of scientists who work at the science policy interface have noticed that governance is lagging horribly behind our technological innovation. Now, I don't expect governance to ever catch up. In fact, being on the edge of the new means in some ways that there's always going to be something ungovernable about it, which is why I think responsibility is always going to have to be a big part of it. You can't just depend upon external regulatory agencies to make it work. But if everything feels like it's accelerating and getting away from us, slowing down is probably an okay thing.
Slowing down science sounds like, one, very hard to do. It kind of feels like a runaway train at times. And two, like something that people aren't going to want to do. Is there really appetite for this and response within the community?
I think one of the problems with slowing down science is all the incentives within scientific practice and scientific research are currently stacked towards publish faster, get your paper out the door. That's how you get credit. That's how you get priority. You have to make the discovery first. You have to get the paper in Nature and in Science. So there are all these pressures to do it more quickly. But I think over the past 10 years, we've seen a lot of the costs of that. So a lot of the concerns over scientific replication are driven by the desire for speed. A lot of concerns over scientific fraud are driven by the desire for speed. So I think the scientific community, even internally, is already seeing the problems with this continual pressure to publish more and more and more, and wondering about how do we take the pressure off that. But I think the same can be said for the broader societal context, that if scientists want to continue to experience the support of the public, then they have to not just produce results that are reliable and not fraudulent, which is, of course, true, but they also have to think about the relationship between science and society and the implications of their work for the broader society.
And practically, are you hopeful that this can happen?
Yes, but I'm a terrible optimist. So it's a blind spot of mine. It probably makes it easier for me to do my work, but I can't tell you that I think that's grounded in a robust data set. But in my conversations with scientists over the past 15 years, it seems to me that scientists are increasingly aware of the complexities of interfacing with society and are willing, with assistance, to begin to take these things on.
That was the University of Waterloo's Heather Douglas with a plea for slow science, an idea that does seem to be at odds with Hugh Hunt's battle against climate change. So how do we balance the books? Maybe it's a matter of a more nuanced approach to scientific regulation in general, taking into account how far down the road we are for each risk and acting accordingly. Whatever we do about existential risk, I can't emphasise enough how unlikely most of these scenarios are, and mass panic over minute possibilities does not seem helpful. In the words of Sean O'Hegarty, if we're concerned about our house burning down, the least we can do is not leave the oven on.
Wise words indeed, so make sure you turned it off. That was Connie Orbach, and she was speaking with Sean O'Hegarty, Hugh Price, Hugh Hunt, Adrian Curry, Cailin O'Connor and Heather Douglas. And that's all, folks, but do join us next time for one of our Q&A extravaganzas. You send in the science questions and we send you back the answers. If there's something you'd like to know, you can email chris@thenakedscientist.com. We'll also pick up your questions from Twitter @NakedScientists, or you can find us on our Facebook page as well. The Naked Scientist comes to you from Cambridge University's Institute of Continuing Education. It's supported by the STFC, the EPSRC and Rolls-Royce, and I'm Chris Smith. Until next time, goodbye.